All right, let's get this show on the road. So, I've been doing a lot of thinking. Yeah, full stop. And part of my thinking and research and watching stuff has led me to come to category theory. I mean, it's okay. In this video, you can see it down in my bottom left, or at least you can try to see. I don't know how good my quality is right now, but it is currently 11:35 p.m., and I am not going to end this video until I can confidently say I understand a decent amount of category theory. And in particular, this statement over here, which states that a monad is a monoid in the category of endofunctors. And I will zoom in here just so the page is actually visible. Because what the hell does that mean, right? I do already have a decent idea, I would say, because I have been doing a bit of research into this recently, and also I'm not like, uh, let me just make sure this is actually a good setup. Yeah, I'm not completely new to functional programming in general. I've done some research into category theory in the past, just out of personal interest. And yeah, for some reason I've been drawn back to it recently. So that's yeah, that's the video. Maybe after this I'll turn this into like an edited thing, but for now this is going to be just an unedited recording of me for the vibes. So what do I have so far? Well, let me try and just explain what I kind of understand so far. So for category theory in general, from what I understand, category theory, and I will not look at Wikipedia here. Category theory is the kind of like it's a branch of mathematics, right? Which kind of is like the set theory applied to everything, if that kind of makes sense. Like, I mean, in particular, I got very interested in category theory, not just because of functional programming, but because in my university course, we did set theory. And I was like, huh, a lot of these concepts from set theory, not only do they apply to category theory in some regards, but they also kind of apply to bloody everything, right? You look at probability and you see sets, or you look at I don't know, like proofs of the natural numbers, and it's like, wait, it's all sets? Always has been. You know, like zero is the set of empty sets, or like zero is the empty set maybe, and like one is the set of empty sets, and two is a set of empty sets. Like, I mean, that's just one proof, but like my point is sets are everywhere. And category theory is like making connections. You know, it's like pattern matching, or like sorry, it's like pattern recognition, the science, all right, or like the maths of pattern recognition, because you kind of just mapping things between each other. So that's my understanding of category theory. I'm sure there's like a much more technical definition, but I will get into that in this video, won't I? By figuring out what it's all about formally. And to verify this, let's just have a look at what I actually wrote previously. So I do use Obsidian, and this is these are my alt notes for category theory. I have no idea. I haven't looked at these in like a bloody long time. Um, so let's see how they hold up. So I will zoom in here as well, and also hide this. So category theory is a branch of mathematics, okay, that studies mathematical structures and their relations to each other. Okay, now that's already a bit vague and hard to understand, but okay, like what is a mathematical structure? I should probably really put this in like links. In fact, what I will do is add questions, which is a habit I want to do just generally for Obsidian, so I can like kind of revisit things later. But one question is like, what are mathematical structures in the first place? And we'll see if you can answer most of these in this session here. And their relations to each other. Now, relations is a well-defined concept. There is the mathematical concept of relations, which we also studied in university. And these are relationships between sets or within objects and sets, let's say. Now, I don't know if the relations here is necessarily this, but I assume it must like be linked to some extent. But we will come back to that later, I believe. It is used in functional programming, so it does. I think just for saying that, I should probably extend this to a different space, particularly through its use of functors and monoids. Yes. So I do actually have notes on what a functor is. So the idea of well, first of all, from what I recall, a functor is a mapping of one category to another, or one set to another. Because like, I mean, it's kind of in the name. Like you kind of think, okay, it's called a functor. It's probably related to functions, and I believe that's correct. Because like a function, like let's say I have a function +3, right? It maps a let's say it maps a real number to a real number. So it takes an input, real number, and then it does some operation, add 3, and then outputs a real number. So therefore, the function can literally be defined. If I write it out here, in fact, I'll make a sandbox. It can literally be defined as like a function. Um, okay, this is really, really, really. Okay, yeah, something like this. This is not the formal. Actually, this might be the formal way of writing it, but like it's a function that takes that's natural number. I mean real number. A function that takes a real number, um, and returns a real number. So like that's like kind of a function. And then from my understanding, a functor is just the exact same thing, except instead of taking a real number, it takes a category and maps it to a category or a set maybe. Well, no, because a set would be a function. So I'm guessing it must be categories. So let's have a look. The idea of a functor. Oh, and by the way, when I read out these notes, it was mainly through the lens of Haskell and functional programming. So, like in this video, although I do want to get into, but like look into why or how it works for functional programming, I particularly want to understand the actual category theory as well, because I think that's quite interesting. So, what did I write? The idea of a functor originates from category theory, but is also defined in some areas of programming, in particular functional programming. Mind you, a functor does appear. Yeah, I mean, I say in this video, there's also a functor for object-oriented programming, but it's really weird. And I'll look into that in a second. So in functional programming, a functor is a container that can be mapped across. This means it accepts functions that can modify the value within the container. Examples of functors in Haskell include the maybe a type, the list type, and the IO type. A great general Haskell definition of the concept would look like significant fmap. Okay, so it's a class functor where you have to have or implement the functions fmap, which takes a function from A to B, and then applies it to an object A and returns an object B. And then this operator, which I forgot the name of, but we can see it takes in an object A, a container B, and then kind of just swaps the B for the A. I think that's what it does. Yeah, so this means the function it must satisfy the functor must satisfy the function fmap that accepts a function. What? The functor must satisfy the function fmap that accepts a function, changes format, blah 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 blah. Already said that. And this would be the definition of maybe. Right. So for maybe, you just say I have an fmap where I take A to B, function from A to B, and then a maybe A and returns a maybe B. And we see here, if it's nothing, it's nothing. If it's something, then it applies it to that, right? So it may be useful to even get out, let's do Godbolt. And actually, no, I'm going to do that. Let's go to just the Haskell playground to kind of play around with this as well. So let's say we want to do print to start fmap. Let's do 5 on maybe 3, and by 5 I mean +5, the function +5, and that should print maybe 8. Where's the run button? Here it is. Exception, because this should be just 8. My bad. Yeah, just 8. So it's taking our thing here, unwrapping it, so we get 3, then doing +5. And this can also be kind of demonstrated through the monad operator. Not that a monad is a functor, but just kind of demonstrate what I already kind of know. I can do this, which takes like that, and that should be the same result. Just 3, unwrapping it, adding 5, and then we also need to wrap it again when we return. Yeah. So same thing here. Um, yeah. If map. Now, something interesting is that when I was first reading about this, particularly, I mean, I was reading the book, what's it called? Programming in Haskell, second edition. I was reading that book, and it's, I mean, I think that's where I got these definitions from. And like, what it didn't tell you is that although Haskell, like, although there are implicit laws that functors must follow from category theory, Haskell does not have the tooling or like the tooling really to enforce those laws. So to say what I mean, right? With this, we have an F map here. We're adding 5, just 3, and then it does what you expect, right? It adds 5 to the thing inside, which is 3 plus 5, 8, right? But all Haskell requires is that it matches this type signature. So I could easily implement a version of fmap that doesn't do this. Like it'll do +5, and then maybe it will apply it twice, right? So then we actually get just 13. It's like, how did that happen? Like there's no way to that actually checks it does what it says it should, um, which is interesting. And I bring that up because once again, this is particularly we will look into this when we look at the category theory side of functors, because those like they're like the laws matter, whereas in functional programming it's more just like a general concept, like a type thingy, whatever. Anyway, um, there's also functors in object-oriented programming, which is really strange, and it's defined as a struct or class that can be called like a function, but stores a value within its container. So it's somewhat similar, but like here, like if we take add 3 and then like pass it to 5, because like we implemented like this add x, we can like define a thing. It's almost like kind of a way of doing generic programming, where like instead of add x, I would do like an add x, like something like adds 3 almost. Um, yeah. Anyway, not gonna look into that today, but that is interesting. Anyway, so that's what functors and things are. Um, that was a functional programming definition. I don't know if the actual category theory definition is matches that exactly. Like I know that it's a mapping, but like I don't think like in my thing, I said a functor is a container that can be mapped across. I don't know if this is true, at least in category theory, right? Like it's okay to think of it as I mean like look, instance functor maybe. So like we're saying that maybe is an instance of functor, or like it implements the functor traits, like that, right? Thinking like Haskell. I mean Rust. Um, so like you can kind of say that it's a container, but like really, like would you say a function is a container? Like it's more of an operation, right? Um, an F like a functor is a category. Like it's not a container; it's a category of functions, I think. And what we're doing, or like at least not functions, but like morphisms, let's say. And what we're doing is we are specifying maybe in such a way that it contains morphisms under the functor class. Hopefully that's correct. We're going to find out. Um, yeah. So without further ado, let me actually break down what the hell this is. So yeah. that's my what I have written so far, apparently. And just to kind of explain this, then a monad is a monoid in the category of endofunctors of some fixed category, right? I mean, it says here an endofunctor is a functor mapping a category to itself. Um, without looking any further, from what I understand, an endofunctor is, I mean, if you look again like Haskell, right? A monad takes a container of something and then returns a container of something else, or the same thing, but like whatever. Like it's the same container and it's just wrapping something like that. That's what a monad does. So an endofunctor is just that. It takes a container or it takes a category, I should say, um, and then it returns the same category. Yeah, like it returns something within the same category. So I guess it makes sense to think about it then, like I mean, like in functional programming, it makes sense to think about it as a category is a container. Like the maybe type becomes a category in of itself, and then if you implement it as a functor, as a monad, whatever, then you're kind of adding the maybe type as a subcategory of functors and monads. Um, yeah. What is a category? We're going to look into that after this. What is a monoid? A monoid, like, see, again, like, because of this functional programming approach, I thought that monoids were an actual physical thing. I mean, like physical in the programming sense, like an actual structure, a data structure. But they're not. They're just a pattern, a category as well. Like, if I remember correctly, a monoid just has requirements that you need to match. And we'll get into those specifics, but from the top of my head, they need to have an identity morphism. And by morphism, I mean like a mapping from one thing to another, which again, we'll get into. But yeah, an identity morphism. So if you apply if you apply the identity morphism to another morphism, you get the same morphism. So like for a monoid of addition, right? And again, like not like a type. Like I mean the operation of addition. Um, in fact, let's just use that as an example, right? For addition, the category that it operates on is, let's say, just the real numbers. Um, yeah, let's say that we have addition specified for the real numbers. So the three things it needs to match is, first of all, the identity, um, such that, like if I have number 5 and then I have a second object, what should that second object be so that the first object is unchanged? So 5 plus what is 5? And it's 0. So our identity, like not morphism necessarily, like our identity thing is 0, let's say. The other one was multiplication, I think it's called, but not like timesing things together, more like a definition for how you operate. So for addition, the multiplication is defined, or like at least it has to satisfy the first category on the second category, which are same category. So two objects, but same category. And you're saying the first object applied on the second object must give the same category as both, basically. So for addition, if I have a real number and I add it to a real number, then I get a real number, and that's why it's a monoid. And then the third thing was um, I think just establishing a set, in which case again is just the real numbers. So cool. Anyway, enough yapping aside. Let's get into this. So we will build our way up to a monad because, as you can see, the definition is quite. It combines a lot of concepts, and usually, if you follow the Haskell pattern, you start at functors, then applicatives, and then monads. So this will be the last thing we come to. Uh, I will be mostly relying on Wikipedia for this, not just because it's accurate, or like it's more accurate to be, it's more likely to be accurate, but also because I've been kind of interested recently, like in how good is Wikipedia for people to learn from. Like, let's say I click on a page like Monad, and I just don't understand anything, right? Even if I don't understand anything, if I follow these backlinks as if they were like prerequisites I should read up on, should I understand the topic? So that's what I want to know, and that's why I'm specifically on Wikipedia here for most of this. But if that fails, I have this Reddit post here, which I will definitely look through at some point, just because I'm curious to see how this guy presents it, because he has literally gone through the whole thing in one post. Plus, you got comments as well, and then there's also this book, the category theory for programmers by Bartosz Milewski or Milowski, whatever, um, which was actually quite recent, right? 2019. But this is focused on programming, so definitely would like to look at this after the fact, like after I understand category theory in general. But it would definitely be good to look into it later, just kind of see how it's like implemented. Oh, functors in C++. We'll look at that later for sure. Okay, let us begin. So, in mathematics, a category, sometimes called an abstract category, to description for, okay, already getting fucked, is a collection of objects. Okay, so we have our objects, and the category is a collection of them that are linked by quote unquote arrows. Now, this is just so funny to me because, like, if you really break it down, it feels like category theory is just such a simple thing, um, which is why you get like phrases like a monad is a monoid in the category of endofunctors. Like, it probably is really simple, but just the amount of prerequisite knowledge you need to have built up to understand it is quite big. Which is why when we go to the root of a category, we get it literally says it is a collection of objects that are linked by arrows. Like, it's actually quite simple, at least to start with. Of course, I might be biting my tongue later. Um, okay, so we have an abstract category and a concrete category. A concrete category is a category that's equipped with a faithful functor to the category of sets. Okay, so I mean, just based on English, and abstract means more general, right? Whereas concrete is more defined, more specific. So we'll probably get to concrete category later. Um, but notice how it says a collection of objects. What do you know? What else is a collection of objects? Sets, right? Like the set of real numbers is a collection of objects, but the objects are just numbers. Which is interesting. Are they linked by arrows though? I guess not. No, they are. Sorry, it says a collection of objects that are linked by arrows. Yes. Okay. So here the image is helpful. We can see that we have functions that map from like A to B, B to C, and the whole thing is a category. Which makes you question then. So A and B and C are objects, right? So in this case, A, B, and C are probably sets, I would imagine, or at least like sets fall into it. Yeah, it says here. A simple example is a category of sets whose objects are sets and whose arrows are functions. Okay, so like literally, like, but that's an example. So it doesn't have to be sets. And again, like I find it so interesting because you have set theory, which seems to apply to so many things, and then you have category theory, which is like a step above. Like it's the sets of sets, right? It's the abstraction of the abstraction. Um, and I mean, I'll say this now. Again, I don't think this is hard necessarily. Like I think I don't think it's complicated. I think it's actually quite simple, but just the amount of like abstraction, like your ability to abstract and just step back and see the big picture, that's the real difficulty, which is quite cool. Um, okay, so a category has two basic properties: the ability to compose the arrows associatively, and the existence of an identity arrow for each object. Okay, so two concepts that I know will come up a lot for sure: associativity, if I even said that right, and identity. So for associativity, yeah, I said it right. Love this pop-up feature, by the way. The associative property is the property of some binary operations that rearranging the parentheses in an expression will not change the result. And I do have this in my notes, I think. Yeah, I can't spell. As I assume I do. Uh, 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 I think like quaternions, complex numbers, extensions. Yeah. Yeah. Okay, now that's commutativity. That's different. Associativity I haven't looked at, but here I say associativity is such that A times BC should be equal to A times B times C. Or like better rather, A on B on C should be equal to A on B on C. Great. Great. Okay, so let's go ahead and expand this into an actual note here. I will be taking notes throughout this because I think that'd be a good way to actually consolidate this knowledge. Okay, so in mathematics, associativity is a property between what? Binary operations. Okay. Yeah. So it's a property of binary operations. I think I'll make a note for that in the future. Binary operations such that the parentheses, what the order of parentheses matter. Yeah, such that the order of parentheses do matter. And let's go ahead and add some aliases for these. So we have the associative property. Yeah, associative. So I have to be careful I'm actually spelling these correctly because for some reason my keyboard's a bit messed up right now. So I can make typos pretty much any time. Let's have a look at some examples. Okay, so for example, 2 plus 3 plus 4 equals 2 plus 3 plus 4 equals 9. Okay, 2 times 2 to the 4, yeah. So even though the parentheses are rearranged on each line, the values of the expressions were not altered. So to give some examples, for addition, we can have 2 plus 3 plus 4 is equivalent to 2 plus 3 plus 4, which is 9. Or for multiplication, a closing thing there. Multiplication, we can have 2 times 3, or 2 times, yeah. Sorry, 2 times 3 times 4 is the same as 2 times 3 times 4. I mean, it's very intuitive. Like anyone who's done like basic maths in school will obviously know this. But just defining it is really important, and just like understanding, like being able to give it a label. And like again, I mean, I've said it a lot of times. I'm saying it a lot of times again. This is probably really simple. It's being conscious of it, such that you can apply it to abstract other things. So 2 times 3 is 6, times 4 is 24. Ooh, yeah, and let's just make these collapse by default. Okay. So this is not the same as commutativity. So that was my other notes. Commutativity, not China. Communist. How do I spell commutativity? Commutativity. Commutative, yes. If something is commutative in mathematics, the order in which they are written does not matter. Okay. Just standardize this. How did that even happen? Multiplication. Yeah. So not the same. Okay, so it's specifically about parentheses. Okay. This can apply particularly to function composition and matrix multiplication. Do I have notes on matrices? I don't. Okay. Matrix multiplication. Cool. So we know that arrows are composed associatively. So we'll see what that actually means. And the existence of an identity arrow. Now the identity is, I mean, there's not even a link for it. There probably could be, but like it just means that it doesn't change, right? Like I think 1A, like the one sub A means the identity, such that if you apply this to itself, like here, if you apply the function f to A, you get B. But if you apply the identity function of A to itself, you get A. So I will actually write this down in a note if I can think of how to just like write it in a way that makes sense. And it's good to write this down because like although it seems obvious, being able to express it in words is really important. So we'll say the identity in mathematics. So in mathematics again, the identity is a mapping of an object onto itself. For example, well, yeah, for example, so to give an example, let's say we have addition again. So we have addition. So for an input, like an operand, but like for an input 5, the identity function that gives the same output of 5 is, of course, f of x equals x. But if we have an operation, say division, and I'll put a full stop here, sorry, separate these two ideas. But if we have an operation, say addition, that is defined in the form f of x equals, well, f of xy, let's say, equals x plus y, and we must comply to this form, then we can define the identity function for addition as f of x equals x plus 0, where y is just implicitly 0, let's say. Yeah. Okay. And then category theory. Now, I will actually look at this first before going any further, but this is the first paragraph here for category. Cool. Category of sets. There's a whole page for that. Okay. Sets theory. Don't need to get into that too deep. But this is a category with a collection of objects A, B, and C, a collection of morphisms denoted F, G, G of F, and the loops of their entity arrows. So I'm curious to know what morphisms are. I mean, like, obviously, like they, like in this case, they're functions. But like, morphism must be a more general thing. Because like in maths, especially in like school, right? You learn these things like functions, sets, objects, I guess. But category theory, because it abstracts above that, um, you kind of they use different words. Like they could use the word function, I guess, but instead like a morphism is like the abstraction of a function, or like the higher order of a function, let's say. And like a category is the higher abstraction of a set. So like there is some kind of mapping, ironically. Like you could probably map the relationship between category theory and set theory. Um, and I would actually like to see that, but it may help to think about that. Like here, it literally says a simple example is a category of sets where the objects are sets and the arrows are functions. So like we can think of it in that way. Okay, but the arrows are morphisms. Good to know. And the loops are the identity arrows. So identity morphisms, which is good to know. This category is typically denoted by a boldface 3. Okay, so already I'm inferring that the category with a boldface 3 is just a category defined such that you have a morphism of F from A to B, a morphism G from B to C, and then a morphism G of F that is A to C, and then identity morphisms. And what this does is it represents a model of some kind of thing, I guess, that fits this. Because like in category theory, like people ask like, what is category theory useful for? Right? Like, oh, like how do I use it? Like it's not really something you use per se. It's more something you just apply. Like it's noticing patterns between things and then defining those patterns, and then you can like define things from those patterns. Like it's useful for creating models, which is what programming does, right? Like in Rust with the trait system, you can define traits which are like models of what functions should be in it. Or if you're from like Java or a C++, you might think of interfaces. Like it's kind of like that. Like you wouldn't say, what are they useful for? Like, well, you don't need them, but they're good for just kind of creating a model, of like consistency and like reusing patterns and kind of stuff. So let's get into actual what is category theory. Category theory is a general theory of mathematical structures. Okay, so now we actually have this highlighted. In mathematics, a structure on a set refers to providing or endowing it with certain additional features. Okay, I will need to look into this. And their relations. Okay, so relations mentioned. I mean, I think I literally copy pasted this definition. I'm not gonna lie, because what the hell? That's literally what it says here, isn't it? Let's go category theory. Yeah. So in mathematics, a structure on a set or sets refers to providing or endowing it or them with certain additional features. So an operation, relation, metric, or topology. Topology. Ooh, that's come up. The additional features are attached or related to the set, so as to provide it with some additional meaning or significance. So possible structures are measures, algebraic structures, topologies, structures, orders, categories, setoids. Bloody hell. Differential structures, events, and equivalence relations. Okay. Um, interesting. Interesting. Okay. So I'm going to create a page for this. Mathematical structure. Okay. So we have mathematical structure uh, in mathematics, or rather a mathematical structure is, or on a set, sorry. Um, hmm, okay. Is the, hmm, is the addition of certain features to a set. Um, so as to provide them with, yeah, like additional meaning or significance. I will copy that verbatim. And then, for example, one that sticks out to me is orders. So orders, order, like okay, well I do like this. Order. So sets by default, let's say, sets by default are unordered, but they can be, but an order can, but they can be provided an orderal system. That's not a word. Let's say a system of order. Order theory, goddamn. A system of order. Okay, if I ever want to get into that later. Or for another example, sets can be extended, not extended, but like sets can be given relations, right? Uh, equivalence relations. Does it have to be equivalence relation? Oh, okay. I'm not sure of that one then. So, oh, ow, Jesus Christ. Sometimes a set is endowed with more than one feature simultaneously, which allows mathematicians to study the interaction between the different structures more richly. Sorry, I need to zoom in here. For example, an ordering imposes a rigid form, shape topology on the set, and if a set has both a topology feature and a group feature, such that these two features related to blah 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 blah. Okay, topological group. So this is very interesting in of itself. But we won't get into that just now. But holy moly, morphism mentioned, a map between two similarly structured sets that preserves their structure is known as a morphism. Morphism mentioned, and such maps are of special interest in many fields of mathematics, such as homomorphisms, which preserve algebraic structures, continuous functions, and differentiable functions. Uh, cool. Goddamn. There's some examples, which I will look into this in a second. But okay. So yeah, a morphism is a map between two sets. Which means a category is just a set, right? Like, is it? I mean, for anyone who's somehow watching this video, what is a set? Or like, sorry, is it fair to say that a category is a set? Because I feel like a category is just a set, but with a different name, so as not to confuse it with set theory. Because this very much sounds like it's like when it says set, I assume it can refer to categories. Um, in fact, let me just do a search on this page. For the category of sets, it has different. Category of sets, objects of sets, and motions of functions. Okay, so I don't know. You know what? Let's ask Claude. So, is it fair to say that sets, or that categories in category theory are sets, but just with different names, so as not to confuse with set theory? I mean, I think no, because as you saw from the category, it included functions and morphisms, but okay, not quite. Yeah, at first glance, you can look that way. Categories, objects, morphisms, and it's what categories, blah blah blah. Okay, categories aren't defined by membership. Logical are not sets. Philosophy is inverted. Categories can be foundational alternatives to set theory. Oh, some mathematicians following Lovere have proposed grounding all of mathematics in category theory rather than set theory, which is very interesting. So they're different, but one can replace the other. Now that is fascinating, because what if category theory was taught in school, right? Like I do wonder, because like it's so abstract. Like surely that would be useful. outside of just maths, but like in life in general. Like how much easier of a time would people have learning like Haskell if they already knew what functors were, right? And monads and all that. Um, Objects are sets, morphisms are functions. Okay, so like a category contains functions and sets, or it can, I guess. A set is its elements. Categories are built on morphisms. Oh, okay. Okay, so a category is specifically the relations between sets, let's say, whereas a set is the objects. Okay, cool. Makes sense. So let's go ahead and write this down. Um, yeah. So the mapping of one structure to another, well, from one set. Yeah, okay. From one set to another, where structure is preserved, is a morphism. Is a morphism. Polymorphism. It'd be hilarious if that's actually the same like thing. Idea. Okay. So we will define what a morphism is. Um, in category theory. We'll see if we can come to that later. In fact, can I open this in a new page? Yeah. Okay. And for the example, the set of real numbers has several standard structures. An order, that is true. Algebraic structure, in fact, let me write this down as well. Yeah, so the real numbers are an ordered set, as every number is either greater than or less than any other. Ignoring infinity, but whatever. Yeah, and I'll link this. What's real? Real number. What? I have a link for real number. Do I not? Okay. Okay. Um, yeah. Algebraic structure. So the operations of addition and multiplication. Oh, okay. So when it says algebraic structure, it means operations, and that can form a field. Okay. So did it say that here somewhere? Yes. Homomorphisms. Oh, it said home. Okay, I kind of just glossed over that. A homomorphism is a structure preserving map between objects. Blah, 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 blah. So there are heteromorphisms, which change the structure. Okay, which reserves algebraic structures, continuous functions. Okay, so algebraic structure, there are yeah. So it's a group theory. For the set theory, group theory, a category theory, like what the hell, and the pair of which together make it into a field. Okay, I mean, like I know about like vector fields, but this means like if you were to take a field of real numbers under addition, then the field is still real numbers, right? Like you can't really get out of that. Or like they're complete under the field of real numbers, stuff like that. A measure. Intervals of the real line have a specific length. Cool, okay. A metric. There's a notion of distance between points. There is. Geometry. It is flat, sure. Topology. Open sets. Uh, don't know about that one. What's it about? With every point P in it, um, Okay. Nope. Never mind. Uh, there are also interfaces. Oop. Interfaces mentioned. Its order and independently its metric structure induce its topology. Okay. Clearly, I need to look into topology at some point. Its order. In fact, let me just make a note of that in my question. Whoa, trillions things to research. Questions. What is topology? Because bloody hell. Can I print this actually? Please, thank you. Where are we? We can close this, close this. Okay. Its order and algebraic structure make it into an ordered field. Okay. And its algebraic structure and topology make it into a Lie group. Well, so these are like derivatives? Like the derived from that? Okay. So that's structure. Um, so category theory is a general theory of mathematical structures and their relations. So the relations between mathematical structures. So what? An example of one is real numbers then? Because I thought that they could apply to because like I mean a real number is a set, right? But clearly they could apply to anything else as well. Um, or like sorry, they could apply to things other than sets, or else they wouldn't say that a set is just an example. Um, like from my understanding, like you could map burritos to, or like sorry, you could do it like category theory for like burritos to cats or something. Like I don't know. I don't know. Let's just read on. It was introduced by Samuel Eilenberg and Saunders MacLean in the mid 20th century in a foundational work on algebraic topology. Topology just keeps getting mentioned. But yeah, from Newton Joseph, algebra to study topology. Dude, what is topology? Do I need to say what topology? Okay, I'll skip topology for now because I can sense it gets deep. But let's see how far I can get without it. Category theory can be used in most areas of mathematics, in particular in particular many constructions of new mathematical objects, which is just an abstract concept. Okay, and from previous ones that appear similarly in several contexts, are conveniently expressed and unified in terms of categories. Cool. Examples include quotient spaces, direct products, completion, and duality. I don't know what any of these are. Completion maybe, but okay. Many areas of computer science, let's go, mentioned, also rely on category theory, such as functional programming and semantics. The meaning of programming languages. I have been meaning to look into. I mean, I literally have this book here. Um, yeah, the semantics of programming languages. I've been meaning to get into it. It does kind of like touch on functional programming actually, and it kind of inspired me to make my own calculator, or like my own my own calculator thing using like trees and stuff. But cool. Um, Semantics is the rigorous methodological study of the mathematics programming languages. Okay. Yeah, I wonder how that comes up here then. I mean, I'm coming from like a functional programming standpoint, but I would if I can understand category theory in general, I would like to apply that to other things as well. Okay. Schematic representation of the object, so this is the same thing, yeah. Commutative diagram. Notice there's no identity function here. Diagrams such are all directed paths in the diagram with the same start and end points lead to the same result. So this leads to this leads to this, therefore this leads to this. Okay. Um, is that what it means to be commutative? Because when I did it, I talked about the order. Should I expand this? Morphisms, objects, or vertices. Okay, so these are like actual things. Okay, in that case, I will actually need to write this down. So can I go through these, blah, 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 easy questions, with easy questions. Where have I written this? So this is So the relations, or like the let's say objects and their morphisms, is that not a word, are typically represented via commutative diagrams. Okay, so in mathematics, what the hell? In mathematics, um, a commutative diagram is a diagram, is a diagram, is one that um, is like it's on like I guess like it's on like it's like rules you could say. Like it's one defined such that all connected paths, let's say, like all paths, yeah, all connected paths, um, with the same start and endpoints lead to the same results. Yeah, no, like I understand what that means. It's just like how do I like I feel like that wording doesn't really sit well with me. Like if it starts at this point and you can follow it to this point, and then this starts at this point and follows to this point, like because you have these arrows, you should also have, yeah, what is it not a mapping from A to E? Huh? Oh, no, no, no. So I think you can say that this maps from A to E or E prime, sorry. Because I did watch a video about this back a while ago. But from what I recall, yeah, it's implicit. So there is a function from A to E prime, but it's implicit. Okay. So say start and endpoints. Okay, so such that any two objects connected through a series of morphisms can also be uh, connected directly, let's say. Um, I could be wrong, but hopefully, if I am wrong, that becomes evident later on. I could like verify with like Claude and stuff, but I'll leave it for now. But like here, in this diagram, yeah, the first isomorphism, whatever, the commutativity of the triangle means that f equals f with a tilde on top on pi. Or for here, with a, b, d, and a, c, d, this means that it says h of f, so h acting on f is equivalent to k acting on g, because this is the same as this, which should be the same as this, because f of h is this and g of k is this, right? So I assume that's how it works. Um, cool. And I will include a picture, preferably with a white background. Um, I could like default this, but whatever. Oh, don't do that. But yeah, Windows added this new thing for screenshots. It's so good. Like, I can actually like choose like the size now. I can draw if I want to. Like, best update in a long time. That or it's an extension I have. But either way. Okay. So big. Can I resize this? Jeez. Obsidian, please add resizing in view mode on God. Right. Let's close it. That's fine. So that's this. Okay. A category is formed by two sorts of objects: the objects of the category and the morphisms. So a morphism is in of itself an object, which relate to objects called the source and the target. Really? So a morphism is a type of object. That's crazy, dude. Okay. Like again, like just like the foundations of this is just huge. Like you really need to understand. So in category theory, a morphism is a structure. Well, I can actually highlight this as well. A mathematical structure is a structure preserving map between two objects. Now, what is an object? Mathematical object. Two mathematical object. Mathematical objects. Okay, you're crazy. Yeah, like homomorphism. Uh, so for example, a function from one set to another set is a morphism, which is cool, right? Because like you think that those are the only types of morphisms that can exist, but no, there's more. Um, Furthermore, a morphism is in of itself a type of object. And then I guess therefore you would infer that you could apply a morphism between morphisms, right? Called the source and target, it says. Called the source and target. So can a morphism be applied, or if a morphism is also a type of mathematical object, does that mean that there are morphisms between morphisms? Yes. In category theory, a morphism or an arrow. Okay. A morphism, also known as an arrow, which is a really weird name, but you can trust computer scientists and mathematicians to just make the worst names imaginable. uh, so, furthermore, a morphism is a type of object, and thus it is also possible to have morphisms between morphisms. Which is kind of cool because, like just out the box, you have this recursive nature of category theory, which really means because you may think like, oh, okay, so then if category theory is the abstracted set theory, then what's the abstracted category theory? You might ask, and the answer is category theory. Like because it's recursive in that manner, you can abstract upon like category theory can abstract upon itself, which is really cool. Um, and to kind of go on the side here, I was doing a lot of research into um. Okay, well, I have no tabs open for it right now, but there's like Agda is an example of a language where you can define types through proofs or define functors, I think, or like I don't know, like stuff through proofs. For example, let's say I have I mean the common example is a vector with a size. but like it's at runtime. So like say I want to get a vector slice, specifically of a size 5. Um, so like my function will only allow, like as an argument, it will only accept vector slices of size 5, which is different from an array, right? Because like it's still a vector slice, not an array, but like it has a fixed size, and the only way that you can pass a vector slice into that function is if it has a a 5, a size of 5. Um, and you may think, well, can't you do this in any language like Rust or C++? No, you can't. You can't do that because it's compile time. And the way Agda does it, I think, and I think Lean as well is an example, is they do it by having proofs. Like you need to formally prove that when you pass this slice into your function, it has a size of 5, which is really interesting, really cool. And I bring it up because that's like the final level in a way. Like in Haskell, yes, you have functors, but they're not enforced, which I think I might have said earlier in this video. Like there's no way for Haskell to actually enforce them, those laws, the functor laws, because it just doesn't have the tooling for it. But Agda can do it. Agda, like not like necessarily like intentionally. Like its focus has been like Lean is to like make proofs, but they have also ended up making functors provable, right? Like something that can be enforced by the language. It's slow to execute and therefore not very practical, but it is possible. So, and that's cool because it should mean, because of again like category theory's recursive nature, it should mean that if a language successfully implements it in a practical way, then it would be like the possibilities would literally be boundless. Like the possibilities for abstraction from like a functional standpoint would just be limitless. Because like right now you can't, like in Haskell or even Rust, you cannot specify laws for a functor. You can give a type signature, but someone can break those rules. Um, but imagine if you could enforce those rules. That'd be crazy. That would be crazy. And it means that you could have, functors upon functions, but then also functors upon functors, and then functors upon those functors, right? Because again, it's recursive, so you can just keep on going. That's why I understand it. So that's cool. And this is a prime example, right? A morphism is an object, and I believe a category is also an object, which I will actually look up here. But first of all, given a category C, you can construct its arrow category, where objects are the morphisms of C. Morphisms are commuting squares. Yeah. Um, Objects categories. So cat. Yeah. So cat is the category of categories, which is a two category, where you have one morphisms, which are the functors between categories, and two morphisms, which are natural transformations between functors, which are morphisms between functors, which are morphisms between categories. So it's turtles all the way down. Wow, I can't believe you just used that phrase. Um, yeah, mathematicians just stop here. Infinite categories. So there are infinite categories. So yeah, it is literally recursive. It says your intuition is exactly right. It's a core theme in category theory. Anything that can be an object can be morphed between. So categories are also objects. Let's see what it says to that. Yes. And this way it what? Dizzying. Genuinely dizzying. Cat is the category whose objects are small categories. Oh my god. Okay. I mean, this shit is deep, man. Um, okay. It's not just a curiosity, it's a genuine foundational tension. If every collection of mathematical objects forms a category, and categories are mathematical objects, then you risk something analogous to Russell's paradox, a category of all categories that contains itself. Oh my god, interesting. So cool, dude. I mean, I don't study mathematics. Maybe it's because I was taught, like, I don't really see it being that interesting to like study like in university or whatever. But category theory is just so interesting. Like I love, I absolutely love to study, to learn more about mathematics through computer science. I think that's really cool because like there's definitely a link between not just like computational theory, but the actual theory of like designing programming languages, because it's working with like linguistics as well. Um, so if you like computer science, math, like it's all connected. It's all connected. It's great. So a morphism is often represented by an arrow from its source to its target. Okay, so let's go ahead and take this image as well. Whoops, I made a note. No, I don't want to do that. Just remove the background colors here. Oh, shit. Gotta get used to this now. Uh, yeah. Uh, okay. Morphisms are typically morph. I'm spelling it correctly. Dude, like my body auto check is just so bad. My auto correct. Morphisms are spell check. Morphisms are typically represented by literal arrows from one object to another. Yeah, close. Thank you. Morphisms can be composed if the target of the first morphism equals the source of the second one. So the target of the first equals the source of the second. So my x here, target of the first. Okay, so here's my morphism. Target of the first is this, and the source of the second is this, which means I can compose them. Yeah, okay. Morphism composition has similar properties as function composition. Similar. Okay. They are often some sort of functions, but this is not always the case. Oh my god, monoid mentioned. Okay, so a morphism between blah 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 blah. Um, like with functions, morphisms can be well, this is different from function composition. Can be composed such that composed. Morphisms can be composed if the target of the first is the same as the source of the second, such that yeah, I mean such a f of yeah, denoted as f. I think of is the word there, or maybe a circ. I think it's circ for latex. Yeah, f of g for some morphisms f and g, as seen in the above example diagram. Commutative diagram. See, I can now link to this. Oh, I love it. It's all come together. Okay. Morphism. Yeah. Okay. So there's associativity laws, and there is the identity morphism. So is that a requirement? Does every single object have to have an identity morphism? Because I remember again in this video I watched, Um, it says not everything can be a category. Like there are laws, and we'll get into it later. Okay, and like I will say, just by the way, I know that in like making these guesses, like I can get to the wrong answer, or I can waste time, let's say, by like asking questions that are going to be answered in the next paragraph. Um, I know it's not time efficient, but just I I mean I've improved this. I've done research on this, like the psychological research, but my assumption is that if I prime my brain, then not only like it's just better, right? Because like it's like I'm really kind of like trying to figure things out. I can reach conclusions myself, which is generally just better for like things sticking. And it also means that I can set myself up for failure. And if I set myself up for failure, it means I will make mistakes. And everyone, at this point, people should know that mistakes are a really good way to learn. So just an aside there, um, to explain why, because I could have finished this whole page right now, but I do want to actually think about this and see what I can kind of infer from each step. And so far, I will say Wikipedia is doing a good job. Morphisms are often some sort of functions, but this is not always the case. For example, a monoid may be viewed as a category with a single object, whose morphisms are the elements of the monoid. Interesting. So it's called a monoid because it is literally a monoid. um, maybe. Hold on. Monoid etymology. Because what's a name? Monos and the suffix oid, the likeness of, similar to. Okay. It contains a single identity element. So a monoid may be viewed as a category with a single object whose morphisms are the elements of the monoid. What does that mean? um, Also, like, when is it not a function? Like, I don't understand how that's not a function. A category with a single object. So a monad, right, is a monoid. So maybe it helps to think of it in that way. Like, let's say I have the maybe type, and maybe that's why. Ah, yeah, because I was thinking at like towards the beginning of this video. I have a gift. What the hell? Okay. I have I was thinking at the beginning of the video. Like, it seems like in functional programming, a category is just an object, right? Like a collection is just an object, but that's probably just because I'm looking at monads, and monads are categories with one object. So that kind of makes sense, doesn't it? It's like the maybe monad, right? The maybe monad um, is a single object. Okay, so the morphisms are elements of the monoid. What does that mean? Okay, so I don't fully understand this without getting into what a monoid is yet, but just to say, um, sure enough, um, morphisms are usually, does it say usually? Often, are often um, functions, although not always, like with monoids. Yes, sir. Okay, so that's the first fundamental concept. Okay, the second fundamental concept of category theory is a functor. Wait, I thought a morphism was a functor. Okay, hold up. Which plays a role of a morphism between two categories. Okay, category 1, category 2. It maps objects of C1 to objects of C2 and morphisms of C1 to morphisms of C2 in such a way that sources are mapped to sources and targets are mapped to targets. Or in the case of a contravariant functor, sources are mapped to targets, vice versa. Okay, whatever. And the third fundamental concept. Whoa. Can we just like understand that first? Okay, fine. I think a third one is that natural transformation that may What is a natural transformation that may be viewed as a morphism of functors? Oh my god, already so lost. Okay. Do I have a? I mean, I think category comes up later. Um, let's get into that, I guess. Um, okay. I mean, this is the overview, so obviously I'm gonna be a bit stuck. And it does explain them in more detail here, but I'll see what I can get from this page alone. So morphisms are often so morphisms are often some sort of functions. Okay, no. A functor plays a role of a morphism between two categories. It maps objects C1 to C2. Oh, between categories. Oh, okay. Oh. So a functor is just a morphism between categories. Between categories, because categories are objects. Yeah. Did Claude say this? So if I have so are functors just morphisms between objects that are categories? Oh my god. Yes. Holy shit. Like I'm actually getting quite good. Okay, so sure enough, moreover, morphisms between categories. If I mentioned, I have not mentioned categories yet. So between categories, does it say man naming conventions, dude? Mathematics. Okay, so categories. Morphisms between categories. Um, since categories are two objects, are also objects. um, or a type of object, let's say, are known as functors. Let's go. And I do actually have this. Yeah. So in category theory, a functor is a morphism, and now I can use this word because I actually understand what it means. A morphism, I actually understand what it means. Sorry, a morphism is between two categories. So the idea of a functor is also defined in some areas of programming. Okay. Um, slightly different to the mathematical. Uh, understanding, let's say. Okay, let me just add some analyses. Do I have nothing for mathematics? Holy moly. Um, I need to really start doing my notes more. Like this video is like the first time I'm really sitting down to like properly expand my notes in a while. Mathematical, math. Okay. So the one I didn't understand really is a natural transformation. I mean, it says it's a morphism of functors. Um, which like fair enough. So yeah, from what I understand, this goes a level higher with natural transformations, um, being morphisms between functors. So are there morphisms between Natural transformations too. Just how high does it go? Unless my premise is wrong, but okay, it's not wrong. Are we joking? Higher category theory, dude. I love this. I actually love this. Natural transformations are two morphisms in cat, and yes, there are morphisms between them too called modifications. Three morphisms. The tower is real and never terminates. Wow. Hmm. There's more here. Okay, so it goes quite interesting. Groupoids and all that, but let's not get into that just now. But I will make a note. And since functors are also objects, morphisms between functors are known as natural transformations. But those two objects, um, and they are known, and morphisms between those are known as, what did I say, modifications. Oh my god, modifications. And the chain goes up and up to infinity. That's crazy. That is crazy. I mean, like it's not shocking, um, per se, because like obviously I was able to kind of conclude this, but like it's just wow. Like it's just like it's not shocking, but it's just a bit like what's the word? Awe striking. I don't know. I'm in awe. I'm in awe. Um, yeah. If I was writing this Wikipedia page, which I mean I technically could, right? But like if I were to edit this, I would probably just mention like here the fact that a function is an object and this is an object, because like this is like kind of a, I mean, assuming that clone is lying to my face, and I'm not interpreting it wrong. Like this is a bit too, it hasn't abstracted it enough. Ironically, like it's not big picture enough. Okay, so then for categories, objects, and morphisms, let's go. What is a category? A category consists of the following three mathematical entities: a class object, which is a function for some reason, whose elements are called objects. What? Yeah, see, this is not great. So, what is a class, first of all? A class is a collection of objects that can be unambiguously defined by property that all its members share. I do wonder if classes and like object-oriented programming come from this. I mean, it must. I mean, obviously, math is like really old, so I assume it must do. Like a class contains objects. Yeah, makes sense, doesn't it? Um, Not really though. Like a class is a kind of like a map, is a, like when you instantiate a class, it's more like a blueprint. So that's not really accurate, is it? Nah, whatever. Um, so how do I say this? There's a class of C whose elements are called objects. So the class is called obc. Like, is there like a way to actually say that? A class homc whose elements are called morphisms or maps or arrows. Um, okay, so I guess maps is another synonym. Each morphism F has a source object A and target object B. The expression F to A of B would be verbally stated as F is a morphism from A to B. Cool. So for morphisms, let me go ahead and do this. Denoted by F, so F of A to B. Yeah, I put this here. The expression, yeah, the expression hom AB, so there's two, or hom C of AB, because I guess that was category. Sure. More AB or C category AB, okay, denotes the hom class of all morphisms from A to B. Interesting. So it's like a relation. So hom class is a relation, right? So why is it hom? Like I see like MOR like here, like that's obviously morphism. Hom is like what? Like a homomorphism, maybe. Um, okay, denotes the hom class of all morphisms from A to B. Cool. Is that important? Not really. It's kind of self-explanatory. A class whose elements are called objects. So yeah, I don't understand the class. Like you don't really see the class in the diagram. So let's open this in a new tab real quick. A class is a collection. Oh, it's part of set theory. Okay. So serial numbers, what the hell, are a proper class of objects. Okay. Yeah, okay. I don't understand that. So those are the first two. So objects, morphisms, let's say, and then a binary operation composition. So that for any few objects A, B, and C, we have that a composition is defined such that the morphism of B to C crossed with the morphism of A and B produces the morphism of A to C. So the composition of A from F of A to B and G of B to C is written as G of F or GF, governed by two axioms. So there's the associativity law and the identity law. Oh, this actually has a page. Nice. Called the entity morphism for X, such that for every morphism A to B, we have 1B of F, which equals F of 1A. Great. So again, yeah, I mean, this is the category section, but this is kind of feels more like it feels right to write this under morphisms. Um, interesting. So, did I mention it somewhere? Yeah. Yeah. So the binary operation of composition can be defined such that circ is yeah. Yeah, hom. Why hom? Why hom cat? Oh shit. Okay, that's not what I'm looking at. Hom category. Okay, yeah. So it's short for homomorphism. So what actually is a homomorphism? Structure which have a map between two object functions of the same type. So versus morphism. All homomorphisms are morphisms, but not all morphisms are homomorphisms. Okay. Okay. So text hom of what, AB? No, BC. Why is it BC first? Is there a reason for that, or is it just to emphasize that the order doesn't matter? I mean, we say that the yeah, because we said the endpoint for one. Yeah, okay. Also, this times is interesting because like clearly it's not actually times. Like, and this will come up later as well in like the multiplication thingy. But like clearly they're different. I just don't understand how. Um, but let's use that whatever. So BC times the homomorphism from A to B. It's good to say this out loud so I can really understand what the hell these symbols actually mean. To a homomorphism, they well, yeah, same as a equivalent. I don't know. This notation is a bit weird. This notation is a bit strange. Okay, cool. Good to have that formally. Um, associativity. Yeah. So with composition, we get that it was the E F G H I J K. Oh, why is it backwards? Like I understand, it's just a bit like weird. I don't like it. So composition F um, of G of H is equivalent, or was it equals to? I don't know. Yeah, equivalence and equals to. I mean, again, like I don't study maths formally, so I'm not so familiar with like the. Sorry, this should be the same order. I'm not so familiar with like these words like equivalent, like terms. Sorry, like I don't fully understand what they actually mean, but these are equal. Okay. And the identity. Did I do identity, or did I just? I did. Yeah. So defined such that I love this define such that followed by an equation. So one sub b applied to f is just f, which is f applied to one sub b. It goes both ways. It is associative as well, or it is commutative. Commutative. Yeah, ain't that cool? Okay. Example. A prototypical example of a category is set. What the hell? Prototypical describes something that is the primary standard or quintessential example. I like that. Okay. I would just say quintessential, huh? A prototypical example of a category, my speech is just dying now, is set. The category of sets and functions between them. With a capital S, by the way, and it's in bold. Cool, well, not cool, but like, it is a convention to take note of. The objects of set are just sets, and a morphism from a set to, x to y is a function. Uh, oh, I can highlight this. I can highlight this. The category axioms are satisfied since every set has an identity function, and since composition of functions is associative. Associative, sorry. Oh, okay. So I don't know if I mentioned this then. So, Scheiße. Composition is governed by two axioms. One, well, associativity and identity. Identity. Cool. Morphisms. Relations among morphisms, such as. What do you mean among? Oh, FG equals H. so f1g equals h, okay, are often depicted using commutative diagrams, with points, corners representing objects, and arrows representing morphisms. Sure. Morphisms can have any of the following properties. So a morphism from A to B, or F from A to B, is a monomorphism, or monic. Okay, if f of g1 equals f of g2, which implies g of 1 equals g2, of course. Sure, an epimorphism, oh, what the fuck? Isomorphism? If there exists a morphism g, this is crazy, a morphism g beta a such that f of g equals the identity function, and g of f. What? 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 Generally, what the hell is going on? Yeah, like I know what isomorphism is geometrically. Huh. What the hell? Like the thing with these equations is like they make sense like once you get it, but if you don't get it, oh my god, it hurts. A morphism that's both epic and monic is not okay. Fine. What? So wait, from B to A. So if I apply the morphism F to G, I get the identity function of B. But then also the inverse gives me the identity function of A. Okay, I can't think of an example, but that's interesting. Endomorphism A equals B. Okay. Automorphism, retraction, and section. Sure. Sure, bro. And functors. Functors are structure preserving maps between categories. They can be thought of as morphisms in the category of all categories. Okay. Oh man. Love it. A covariant. Holy moly. Functor F. From a category C to category D, written of a functor of C to D, consists of, for each object X in C, an object f of X in D, and for each morphism X to Y in C. Oh man. Okay, yeah. So there's covariant and contravariant. Wait, so covariant is a default functor, I guess, and contravariant turns morphisms around, reverses all the arrows. So every morphism of X to Y in C must be assigned to a morphism such that the okay, I kind of understand what it's saying, but I would benefit from my visualization. So what have I actually written about functors? Because I mean, like, really, there's not too much to say about functors. Like, it is just a morphism, and then if you want to understand more about functors, then you can just look at a morphism. But like, that's so strange. Can I resize this? Is that a thing I can do? Cannot be found. Yeah, like, why is it so big? Uh, side quest, Obsidian, resize image. Because it's not like wiki, is it? Oh yeah, I need to do this. Ah, so annoying though. Oh, well, no, that doesn't work. Oh wait, is it because I did PX? Yeah. Okay, fair enough. Much better. Let's make this smaller then. Cool. I'm not logged in, but if I was, I would like that. Natural transformations. A natural transformation is a relation between two functors. Notice how it doesn't say morphism. Now, see, the language is the most interesting part here. I mean, not the most interesting, but it is a very interesting part and very important part. Because, like, it just says relation. Like, what's the difference between a relation and a morphism? You know? Are they the same thing? Because, like, there's a mathematical definition of relations, which is not the same as, like, saying, like, a relation necessarily in real life. like a relationship, right? Functors often describe natural constructions and natural transformations, then describe natural homomorphisms between two such constructions. Sometimes two quite different constructions yield quote unquote the same result. This is expressed by a natural isomorphism between the two functors. Dude, this is hard. This is hard to digest, I can't lie. Like, I really need to get more familiar with some of these terms before I can just see them written. Sometimes two quite different constructions yield the same result. Okay. I'm not going to worry too much about I'm not going to worry too much about natural transformations, because as far as functional programming is concerned, or just programming in general, functors are already powerful enough for a lot, and abstracting above that isn't too much more complicated. Like, it is just a morphism. Um, but yeah, some things might become apparent, which is interesting at higher levels, let's say. Okay, other concepts. Limits and colimits. Each category is distinguished by properties that all its objects have in common. That's true. Yet, in the definition of a category, objects are considered atomic. We do not know whether an object A is a set, a topology, or any other abstract concept. Hence, a challenge is to define special objects without referring to the eternal structure of these objects. To define the empty set without referring to elements, or the product topology without referring to open sets, one can characterize these objects in terms of their relations to other objects. Yes, as given by the morphisms of the respective categories. So the task is to find universal properties that uniquely determine the objects of interest. Cool. Was like addition, like the category of. Yeah, but not really. Equivalent categories is a natural question to ask. Under which conditions can two categories be considered essentially the same? In the sense that theorems about one category can readily be transformed into theorems about the other. The measure tool one employs equivalence. Yeah, I wonder if it's like subjective. Okay. For the concepts and results, higher dimensional, yeah, higher category theory. What the hell? I will come back to that later for sure. Two category mentioned. There's a whole page just for two category. That's crazy. Yeah, morphisms, morphisms, biomorphisms. Yeah, 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 yeah. What? Omega category. I saw that just now. Quasi category. Generalization of the notion of a category. Oh man, that's crazy. I mean, yeah, sure, bro. What the hell? So that is. I'm actually getting a headache, and I don't know if it's from like the fact that it's 1:20 a.m. or if it's the fact that it's just this is just really deep. But I am having fun. I am indeed having fun. Okay, historical notes. Okay, yeah, let's look at some of the history. So, category theory was originally introduced for the need of homological algebra. Homology, okay. And then algebraic geometry, scheme theory, like the language scheme. Category theory may be viewed as an extension of universal algebra. Yeah, clearly. Mathematical logic and semantics came later. Topoi, topos, okay, whatever. Feynman diagrams, applied category theory. Computer science, physics, natural language processing, control theory. Cool. So, category theory, that is an overview of that. I took like no notes on actual category theory, but I did answer this question. So instead of relations here, let me change this to morphism. Of functors, applicative. That's not what I did. Applicative. Applicatives. What? Is that our word? and monads. Objects and their morphisms are typically represented via commutative diagrams. Yeah, I mean, I've kind of like put it all into morphisms, haven't I? Um, but like a lot of it does just come down to morphisms. Uh, but there are also objects. So let's just go up here. I mean, this is like the general thing. The main thing is a category. So yeah, a category, which I will not give his own page. I don't think it needs it. Its own note, sorry. Um, is formed by objects and morphisms, both of which are also objects and are denoted by the symbol. Um, yeah, can I view the latex for this? I keep making notes by accident. Where are they going? Here. Okay. I wonder if I can make use of this notes feature because like right now I store stuff here for Obsidian, like all these fucking articles that I just haven't gone through yet. Um, but yeah, so Control I, sorry. I am like I did recently get this Vivaldi browser, by the way. I didn't even mention. Like for those who don't know, this is the Vivaldi browser, Vivaldi, and I have just come from Zen browser because I realized that Zen actually uses a lot of memory, like way more than it should. Um, I was under the impression that it was just a lightweight browser, but no. So yeah, now I'm here and I am loving it so far. It's also Chromium, so I get those advantages, whereas Firefox is a bit harder to kind of have support for. Math Cal C. Sick. And Math Cal C. No need. It's kind of self-explanatory. Okay, we can now move on from category theory. Although I will look at the category page real quick. Um, yeah, what the hell is a concrete category? A concrete category is a category with a faithful functor to the category sets. The functor makes it possible to think of the objects of the category of set as sets with additional structure and its morphisms as structure-preserving functions. Many important categories have obvious interpretations as concrete categories. Okay, so it's for sets specifically. Okay. Um, a collection of objects that are linked by arrows. A category assumes its properties. Yep. Category theory. Okay. So one thing that I find interesting about Wikipedia, like if you look at my notes, there's a lot less, right? Like obviously it's because I'm writing less. Like no shit. There's stuff that I'm just not including. But also between notes, I'm not repeating as much. Whereas Wikipedia does actually restate itself quite a lot. Which isn't bad because it means that you can like get a lot more understanding from a page without leaving it. But it isn't the most efficient, I would argue. Like you could make it more modular, where people need to like jump between pages more often if they want to figure out what something is. Um, and I think a reason that might be as well is because like Wikipedia kind of fears stubs articles. Like if an article is a stub, it isn't considered like people don't want it to exist, basically. But I think like there's nothing wrong with this being a Wikipedia page, really. because like it directs you to the kind of underlying principles in a way, if that makes sense. So, hey, just a thought there. So virtually every branch of modern mathematics can be described in terms of categories, and doing so often reveals deep insights and similarities between similarly different areas of mathematics. Like, why the hell is this here? What? What? Like, it did not say that. It did not say that on the category theory page. I swear. Like that's actually more insight. We should. And virtually every field branch of modern mathematics um, can have deep, can lead, and can lead to deep insights be applied to virtually every field of modern mathematics to wield deep, interesting insights and similarities to otherwise seemingly different areas. And that's like the cool thing. I mean, like I called category theory like pattern recognition, the science or the maths, or the mathematic, whatever. And yeah, like with category theory, you could just connect things, which is such a underrated, underappreciated. Like it's not underappreciated. Like people know that making connections is important, but like they know it, but they kind of ignore it. Like like category theory gets clowned on for being like useless, whatever. But like genuinely, the applications are so important because it's just making connections, and those are really important for learning, for making progress, for engineering, and for programming. I mean, look at the languages. Like Rust isn't you know competing with C++ like just because for like just out of nowhere. Like it's using concepts from functional programming that have been around for ages, and just like yeah, just using them in a way that people will actually like pay attention to them. Like people know that Haskell exists, but like they're free to use it. And I think it's interesting, and it's why I say that like if we taught category theory in school, how like just to think how many more people would suddenly be open to functional programming, right? Um, not that functional, like not to say that I think that functional programming is like the best. Like there's like definitely computers execute functions imperatively or like procedurally, I should say. So like having procedural languages is just better in that sense because it's like more because like in computer science you have the theory of like the abstract theory of maths and you know programming type safety all that stuff, but like there's also the practical aspect of like I need to actually program something and have it work on my computer, you know, um, and like be fast and efficient and like make it use of the assembly instructions and all that. So yeah, there's an interesting intersection that Rust has kind of reached, which is very cool. Um, I mean, like Rust doesn't get it perfectly, obviously, but like it's definitely a step in the right direction, I think. So, yeah, very cool. Um, why does this page have so much more information on category theory than the category theory page? Man, uh, yeah, abstract ways to describe mathematical entities. So category theory is a branch of mathematics that studies mathematical structures and their morphisms to each other, and can be applied to virtually, yeah, is a very abstract, like that very abstractly, let's say, studies. Because like abstraction is just so cool, though, so cool. Um, Like we need to abstract to find new ways to do things, right? Even if it can be slow computationally, the things we can discover as a result are very cool. In addition to formalizing mathematics, category theory is also used to formalize many other systems in computer science, such as the semantics of programming languages. Did I open a page for this? I did, and I closed it. Let's open it again. Two categories are the same if they're the same collection of objects, the same collection of arrows, and the same associative method of composing any pair of arrows. Two different categories may be considered equivalent for purposes of category theory. Yeah. A mapping between two categories compatible with their structures is a functor. Okay. Well-known categories are denoted by a short capitalized word or abbreviation in bold or italics. Yeah. So the naming convention for categories is a short word slash abbreviation in bold or italics, uh, starting with that starts with a capital letter. I know that capitalized means this starts with a capital letter, but like, um, yeah, for some reason I think of like uppercase when I think of that, which is not really the right thing. 2 hours, by the way, 2 hours have passed. I don't know what this is going to do for my computer memory, but I said I wouldn't finish till I really understood it, right? And we're definitely getting closer. Examples include set, yeah, such as set for the category of sets. Yep. Oh, why is there a text? Okay. There are many equivalent definitions of a category. Okay, so it's not fully agreed upon, which I'm actually that doesn't surprise me for something that is so abstract. A category C consists of a class of objects, morphisms, a domain or source class function. Okay, that's new. Codomain, sure. For every three objects, a binary operation called composition. Okay, and the associative law and the left and right unit laws, which is the identity morphism. Yeah. Why is it called left and right? Like this is my issue with the same information being strewn across multiple pages on Wikipedia. Like I do generally think, like, at least so far, this has done a great job of helping to like demystify it. But even as someone who isn't like an expert, but just like, why are we having different things on different pages? Like, while it's good to include things, but like, while I see the benefit of repeating things on different pages, the fact that they're not the same can lead to inconsistencies. Like, obviously this isn't a huge thing, but like, I kind of like need to read all of them to really get the full picture. Whereas it would be better if I could just go to one source and get everything I need, and then it'd be easier for people editing to for editors to contribute and like verify. Yeah, we write. Okay. From these axioms, one can prove that there's. I mean, it says here some authors. For these axioms, one can prove that there's exactly one entity morphism for every object. Often, the map assigning each object is an entity morphism is treated as an extra part of the structure of the category, namely a class function that says uh, object to morphism. What? Oh, that assigns it to its entity morphism. That's cool. Some authors use a slight variation of the definition. Okay. Like, what the hell is this? Unneeded. Required. Huh? Huh? Is there a category here? Small category. Okay. Small and large categories. Oh, look at that. A category C is called small if both the object C and morphism C are actually sets and not proper classes. And large otherwise. A locally small category is a category such that for all objects A and B, the home class, home about, home set. Oh, closure. I'm going to look at what a closure is because I hear lambdas referred to as like lambda expressions referred to as closures. I don't understand why, but okay. A small category can be viewed similar to a monoid. So a monoid is closure, has a closure property. Large categories, on the other hand, can be used to create structures. Okay. Types of morphisms, or you saw these types of categories. Types of categories. Okay, cool. So we can move on. We can move on from the categories. Objects. Oh yes. So a mathematical object is an abstract concept arising in mathematics. Really, typically a mathematical object can be a value that can be assigned to a symbol, and therefore can be involved in formulas. Very abstract indeed. What the hell is real? Truthful not. Sorry. Commonly encountered mathematical objects include numbers, expressions, shapes, functions, and sets. Okay, so literally anything. Very complex. For example, theorems, proofs, and formal theories are all also objects. Really? So like an object is just a thing, bruv. There's a philosophy of mathematics. Nice. Existence, identity, and the nature of reality. Metaphysics, objects are considered entities. Yeah. Okay. Um, did I make a page for objects? Just resize this. Yeah. What's the G/cur? Who cares? Um, Map of objects. Okay, I've not created it yet, but I won't because I'm not sure how to define it. Okay, higher category in mathematics. A higher category or higher category theory is a part of a category theory that at a higher order, which means that some equalities are replaced by explicit arrows. Okay, higher category theory is often applied in atomic topology. Sicko. Um, yeah. Huh? Okay. Interesting. I mean, we're kind of outside the scope of my original focus so far, but just to quickly kind of skim through these. Applied category theory is an academic discipline in which methods from category theory are used to study other fields. Yeah. I love how computer science comes up first. In fact, what does the page even say about computer science? Quantum mechanics. Why is that? Natural language processing, which I love, by the way. NLP. Um, control theory, probability theory, and causality. Okay. Sui. Discoveries. The great insights of computer science. Alan Turing stuff. Yeah, I should really look into these. Wait, programming paradigms. So we got functional programming, imperative, object oriented, service oriented. Okay. AI, of course. Morphological analysis. So cool. Semantics. Yeah, so how is category theory applied to this? functorial semantics uses category theory as the core mathematical formalism. Categorical semantics is usually proven to correspond to some axiomatic semantics that gives a syntactic representation of the categorical structures. Okay, logic. God damn, this goes deep. But like, you can tell, like, there's not even that much like research into these yet. Or like, there is, but like, there's a lot more to be contributed. Um, God damn, this guy's like, it's Oxford, dude. If just imagine if I went to like some of these universities, you could meet these people. Anyway, uh, and a closure. A subset of a larger set is closed under a given operation on the larger set if performing that operation on members of blah, 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 blah. Yeah. Why is a lambda expression called a closure? Oh, it may not be a closure. Okay. Depending on if it has access. Okay. A closure is a function combined with a set of variables declared outside its definition. Oh, never mind then. Okay. We're getting scarily close to, well, let's not speak too soon. So in mathematics, a morphism, okay, so we kind of really looked at this. Um, Morphisms and objects are constituents of a category. Morphisms are also called maps or arrows. So I guess I should write this down as well. A morphism, also known as a map or an arrow. Uh, Partial operation. Or is it partial? What? On the morphisms of category. Okay. Morphisms and categories occur in much of contemporary mathematics. Yeah, topology, bro. God, it's so much. A category C consists of two classes. Yeah, I find it very interesting that like I've written so much about morphisms and it already applies to categories. It's kind of freaky. Okay. Hmm. Okay. A monad. So what is a monad? We have gone over functors, right? So in category theory, by mathematics, a monad is a triple. What is a triple, bro? Consisting of a functor T from a category to itself and two natural transformations, eta and me. That satisfies versions of the associativity and unitality factors. I love that unitality doesn't even have a page yet. Um, someone go get that. Maybe I can do it one day. Um, cool. So if it's a functor from a category to itself, that must mean that T is the identity, right? Surely. For example, if F and G are functors adjoint to each other, then T equals G of F. What does adjoint mean? Like they go back? Equivalence. Okay. A monoid is a monoid. A monad is a monoid in the category of endofunctors of some fixed category. Yeah. So an endofunctor is a functor mapping a category to itself. Yeah. So like, is that not just the identity? No, 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 no. Sorry. No, 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 no. So sorry. I'm wrong. I'm wrong. I'm wrong. I'm wrong. I'm wrong. I'm wrong. If it if it if a functor is if a functor is a category to itself, it is not the identity. It just means that the functor stays within the bounds of the category, if that makes sense. Because like an object to an object would be that. But well, I mean, I guess I guess it kind of can be thought as an identity. But like, there's still change happening. not to the category itself, but like the change can happen to between the different objects. Yeah, okay, whatever. So let's see what a monoid is. That's probably the first thing, and then endofunctors. According to mathematician John Bayes, a monad can be considered in at least two ways. A monad as a generalized monoid. What do you mean generalized? So it's more abstract. This is clear since a monad is a monoid in a certain category. But so why is it generalized? A monad as a tool for studying algebraic gadgets. A group. Okay. Oh wow, it's actually a monad in functional programming. We'll look at that then. Um, theory of data. What? Type theory. Let's go. The denotational semantics of imperative programming languages and functional programming languages, allowing languages without mutable state to do things to simulate for loops. Yeah. They're also called a triple triad. Okay. So let's. Okay, this is quite a lot actually. Let's first have a look at what a monoid is. So in category theory, a monoid or monoid object or internal monoid of algebra with the three components m, me, eta. Oh, okay, so m is here, but in for monad it was just t. For monad it was t. Uh, is that because t goes to itself but m doesn't necessarily? But it does though. Well, no, because that's this. Okay, in a monoidal category. Okay, so monoid is of the form this, but the category contains these. Is an object m together with two morphisms. And those morphisms are multiplication and unit, where unit is the identity. So what's a monoidal category? What's a bifunctor, bro? A monoidal category or tensor category is a category C equipped with a bifunctor that is associative up to a natural isomorphism. Okay, type constructor. Yo, what we doing, bro? What we doing? Okay, so let's go. Do I have a page for monoid yet? I do not. Shocking. So let's go ahead and make one. So a monoid. So a monoid is, well, I guess I can say this. Okay, a monoid is a object, right? Yeah, I mean it says here monoid object. Um, is an object M, just like that. Um, with the two morphisms. I love that I can just link this. Morphisms. Let me just quickly add a alias for this because writing this in plural is driving me crazy. Aliases, morphisms, plural. Thank you. Also map, also arrow, also maps, arrows, because why not? Okay. With the two morphisms, me and eta. Of the form, or like thus of the form. Like it doesn't explain what is this notation, but I can kind of assume that that's just how it works. So boom, 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 and then in the monoidal category of C, which is the category. So math rel, I think it was C. What the hell? Is that XOR? And I. It's not XOR. Okay, I got this wrong already. What the hell? I keep making notes by accident. Control Shift I, not Control Shift C. Hello. There you go. Math cal and O times. Okay. Math cal O times. Where? So yeah, so me is I like this. Me is M O times M to produce M or something along those lines called multiplication. Interesting. This is not given an article for some reason. Uh, Eta is defined as I to M called units. So can we see I in action here? Eta. So eta commute. One is the identity morphism, which is paired with eta, as we can see here. Also here. Um, yeah, I don't know how to actually read this. Like, what's going on? I is the unit elements, and A, alpha, lambda, and rho. Okay. Wow. I don't understand anything here. Okay. Yeah, I think the page has actually lost me. Um, like we're I've already looked at these pages. Like, what do I look at to understand what the hell this is? Um, Wikipedia, please. Okay, this article may be too technical for most users to understand. June 2023, it's been 2 years, almost three now. Okay, I do like that actually has these. This is really cool. Thank you, Wikipedia. But yeah, clearly this is just what the hell? Like, is a page called diagrams and I see no diagrams. Very cool. So like, clearly category theory is a field where like there's still lots of education, I guess. There's also to be figured out still. Like if Wikipedia doesn't have good summaries for people of all, well, not all, but like people who aren't like experts already, it kind of shows that it hasn't really like been formalized enough or like understood well enough by people to really have that concrete stuff. And yeah, okay, holy moly. I might need to refer to this for the monoids. Examples. Okay, a mono object is set. So the category of sets. Um, the unit object I of the monoidal category can be taken to be any singleton. The multiplication me corresponds to the monoid operation in the usual sense. What? The units eta corresponds to the function that maps a single member of I to the identity element of the monoid. Okay. Oh boy, there's more. Huh? Wait, is this important? See, this is interesting because like there's monoid in category theory, and then there's this monoid from abstract algebra, and from what I understand, this one fits better with what I understand. Like it says, it's a set equipped with an associative binary operation. So like for addition, it's be like a plus b, and an identity element, so 0. For example, the natural numbers with addition, okay, as I just said, form a monoid, the identity element being 0. Monoids are semigroups with identity. Such algebraic structures occur in several branches. The functions from a set into itself from a monoid with respect to function decomposition. More generally, in category theory, the morphisms of an object to itself from a monoid, and conversely, a monoid may be viewed as a category with a single object. Like, this is what the hell? I mean, like, I talk about things not being split across multiple pages, but like, what is this? Not this. What's the what? Okay, okay, okay. So a monoid may be viewed as a category. Um, Conversely, with a single mathematical object, or just objects. Um, and is equipped with associative binary operation. So an associative, oh, cool, binary operation, and an identity element. So my assumption is that this multiplication is this. Like if you were to map, if you were to make a morphism or morphisms from monoid to monoid in category theory, my assumption is that there's some functor or some morphism from this the associative binary operation to multiplication, and a morphism from the identity element to a unit. Um, but yeah, I mean, like until I see that explicitly, I can't. Until I see that explicitly, I can't really say for sure. Sorry, I'm just checking to make sure my thing hasn't crashed because it's been like 2 hours plus. Um, okay, it's like what's a semi-group? Yeah, it's interesting that this comes from because it says here set, so clearly like it relates somewhat to set theory, and I find it interesting that that's like the foundation for a monoid in category theory because like clearly sets are and categories are related, like conceptually to an extent. And like what is abstract algebra? A semigroup is a set with an associative internal binary operation. I see. Uh, abstract algebra is modern algebra. Modern algebra. So they are sets with specific operations acting on their elements. Ah, okay. Computer science. The set of strings, built from a given set of characters, is a free monoid. Transition monoids. Okay. Okay. Interesting. Yeah. Yeah. So, like, from what I understand, wait. Okay. Yeah. There's an associative operation and an identity element. So, okay. So here, which is it defines it mathematically, the fold is m. Why is it m star? I don't know. To an m, which is defined with the associative operation if L equals cons M L prime? What? L equals nil? I don't know, bro. I don't know. This is way above my level right now. Um, but like my main takeaway is that there's the binary operation and an identity element. So if we look at a monad again, yeah, like it's a monoid in the category of endofunctors. So a monoid is in the category of endofunctors anyway, but like a monad is a type of monoid. So the monoid can be in the category of endofunctors, and that's called the monad. So let's look at what an endofunctor is. um, okay, take me to the endofunctor page here. Seems like it's not a deep concept. An endofunctor is a functor that maps a category to the same category, e.g., a polynomial functor, for example. Okay. Other ones include the identity functor, which is a type of endofunctor. Good to know. Okay. I can see why I put this in brackets now because it's not even a where yeah here because it's not even a real page. Um, okay. Do I have monad? I surely do. Yeah. A monad is a monoid in the category of endofunctors. Monads are a concept from category theory in mathematics, which also exists as um, a monad is a concept from category theory which also exists as a software design pattern in functional programming that allows computation to be structured as a series of steps. Okay. Yeah, this is a monoid, I believe. Um, and to include an example from Haskell, if I have like a maybe adjust, sorry, 5, I can do just dot plus 3, I do just dot, I don't know, I divide by 2, I guess. And this will give a result of just 4. And that is not a Haskell comment. Yep, cool. Um, I'll put this in its own section, functional programming, or rather just programming, or like even just computer science. Well, I'll say programming. And this should come first. So in programming, in particular from functional programming, monads provide a way for computation to be a series of steps via the chaining of operations. Okay. So now I can in functional programming. Mathematics. Mathematically speaking, a monad is a monoid that consists of an endofunctor T that maps, or that, what's the word? Morphism? Okay, that maps from, well, that is a morphism. Be easier to write. Morphism of a category to itself. Such that, i.e., for the monoid containing object M, M equals T. Yeah. Okay, I like this. That makes sense to me. A triple, sure. Like, why is that not why? Like, I just don't understand why that doesn't have a thing. No. Um, what's the monad in homological programming? Algebra. Nothing. Okay, never mind then. So if FG are adjoint, then T equals G of F. Okay. I mean, this is the basic idea, right? So let me define what endofunctor is. In category theory, an endofunctor is simply a functor that maps a category onto itself. Onto itself. It is particularly well known for um, containing the monad objects. Was there something here? No. Okay. Cool. Cool. Um, yeah. Yeah, it says monad as a generalized monoid. It's not like a specialized monoid, right? Like, I don't understand what that means. I'm just going to ask Claude about this. Why did mathematician John Bayes say that one way in which to consider a monad is if a monad is a, wouldn't the latter reasoning imply that a monad is a specialized monoid, since it's a specific kind of one? Okay. Who is John Bates, by the way? He is alive. Good to know. I thought it said born in 2009. Spin foams, quantum gravity, awesome. What? Oh, I thought he made the World Web quadruped index. Cool, cool. This is a great terminological catch, and the tension you're pointing is a real but dissolves. Okay. So the word generalize here is doing conceptual work in the other direction. A monoid is a special case of a monoid. A monad is a special case of a monoid. It's a monoid. A monoid is a special case of a monad. Monad is a more general concept. Yeah, I understood that, but like I don't understand why. A classical monoid is a monoid in the category set. Yeah, specifically a monoid object in the monoidal category. Is it? The multiplication is a function, and the unit is an element. Okay, a monoid on a category C is a monoid object in the monoidal category. The functor category where so objects are endofunctors. So a monad is literally defined as a monoid in CCO, I mean, composition and identity. Hmm. So confusing. Like, what the hell is this? Right? Like, this is not helping. So why is unitality not a page? Um, okay. I do look forward to reading this Reddit post in a bit to see what the hell, because that might actually help. You're right that there's a genuine tension in the phrasing. If we fix the ambient category, say a monad is a monoid in CC, then yes. Okay. Okay. So I don't understand. Okay. But I think I understand what a monad is, practically speaking. I mean, I already did because it's like denoted by the type signature, which for those who don't know is like um well I think it's characterized by fmap, or at least partially, where fmap is takes a function a to b and no it takes a function a of b. How do I do this? We could Haskell, bro. Take a function take an object a of b, right, and then extract it. Then take what? This can't be right. Okay, well for maybe it's maybe a to a b, and then I think it's outputs maybe b. So if I want to like do fmap takes maybe a and returns an a. No. Take an a, return a maybe a, and then this will be a maybe a. Is this correct? I think this is correct now. So I can take a function that's x to, whoops, just x plus 3, and then apply this to just 5, right? I mean, I do it here, but and then that returns a maybe a. I think this is correct. I will obviously verify this. May fmap definition in Haskell. FAFB. So it's A to B, where FAFB. Huh? Really? I mean, nice. Like generally speaking, F of A, FB. But this returns something else. Oh no, I'm thinking of the monad operator. So I think what I just did. So like this is defined as A to FB, and it takes an F of A and returns F of B. Except it's the other way around, right? Yeah, because like this just returns this, and this is this, which is why we can simplify it as plus 3. And then F of A, then just F of B, that's correct. That's like this works. And then this takes a just, like this is a maybe, whatever, takes a function. In this case, we're doing composition on it. Yeah. Um, monad operator Haskell. MA to A to MB to MB. So FA to A to FB to FB, yeah. I mean F for functor, M for monad. Yeah. So sorry. This is a functor, first of all. And if we go back to our notes, and by our I mean mine, it's a morphism between it's just a morphism. So it just takes a category. So let's say F is a category, or an object in a category maybe. We apply it to F. I mean, in this case, we do to a monoid because there's only one object inside. I guess you could have like a list, but I'm not sure how fmap is defined for a list. Could try it out in a second. But yeah, so we take actually I'll do it now. If I fmap plus 5 over the list of 1 to 5, whoops, let's just cut this out. Yeah, so it applies it to each one, which is interesting. So fmap is indeed, oh yeah, because it maps a category to another, I guess. So then this is another category with different objects. Sure. So yeah, we give the actual mapping to do, and then we just apply it from one to the other. Okay, and then for monad, we're doing will be M. What we're doing is we're taking the category, right? A monad is a monoid, so it's just one in this case, like one object. We're applying a function or a morphism that returns the same category. So this would be this, the endofunctor that returns itself, right? It maps to itself. Um, which is why we have this kind of thing, I guess. And then yeah, it returns itself. Um, cool. It kind of makes sense. I do wonder why you can't do this. I mean, maybe you can. Like if I have a list of 1 to 5, and then like isn't the monad operator defined using fmap anyway? But like here I have this, right? Like can I do this? Like because I get like a list of each thing, and then I need to wrap it. So I guess I would need to do something like, yeah, I don't know how this would work really. Ambiguous available from as a prince. Okay. Yeah, no instance for the monadic operator. Yeah, interesting. Very interesting indeed. Obviously, you can do like an IO um 5, I think. I think this works. Though you can't print it, can you? Or you can't use it. Okay. Anyway, cool. Okay. So yeah, I mean, like I understand how to use monads and how they work. Like it's a way of chaining. I mean, like here I've got the C++ example, which may or may not be correct, but you have like divide and then or else, or like for Rust you have the question mark to propagate errors, but you can also like handle it um in different ways. I don't know. Anyway, it's cool, pretty cool, and I use it in my projects. Well, I use fmap here, but also like to kind of propagate these errors. Like if I look at the main, like I mean, do notation uses it, right? So like that's already implicit monadic chaining. Anyway, monads, very cool. So can I say right now that I understand this statement? A monad is a monoid in the category of endofunctors. Well, I know what an endofunctor is. I kind of know what a monoid is, right? A monoid is just a single object, and it has these things. Um, the multiplication is like a transformation of sorts, and the unit is kind of like the identity. Um, so I can understand it. So that's as far as Wikipedia will seemingly take me for now. At least with my level of understanding. I do wonder what the Spanish says. Wow, it's quite different actually. So let's have a look at the Reddit. But before I do that, actually, let me just have a look at this real quick. Let's see. A monad is a type constructor. What language is this? Okay, this is Haskell. Why do we have two different notations? Cool. That's a font. Wait, the font combines. I just realized. By the way, is Wikipedia using this font? The same one that is recommended for JetBrains Mono. Like yeah. So bind. Oh, so bind. So the bind is the operator. Um, receives a monadic value of type MA and a function f that accepts values of the base type A. Binds unwraps MA, applies F to it, and can process the result of F as a monadic value MB. So kind of like unwraps it, then wraps it again. Yeah, I mean, I do know this, but I'm curious about the specific theory, bruv. You know, theory of types. Regex here in mathematics and theoretical computer science. A type theory is a formal presentation of a specific type system. Really? So it's not like it's just a general thing. I do want to get into type theory. Um, it's pretty cool. But for now, a monad is a monoid in the category of endofunctors. What is the problem? This phrase appears in hilarious, a brief, incomplete, yeah, making fun of the fun. Blah, blah. So I've studied some category theory, I've programmed in Haskell, and I've seen this statement many times before, but I've never actually taken the time to break it down and see why it's true. Okay, a category is simply a collection of objects or points with morphisms. My voice is going, it's getting late. You can compose an arrow Yeah. Okay. So we know what a category is. Yeah, set. Okay. The category Hask, whose objects are Haskell types and whose arrows are functions between those types. So float and int are objects, and round float to int is an arrow. Is this true? God damn. Okay. Cool. Functor is a map. Okay, why did that one render as a link? This one didn't. It's because of this extra bracket. It's a map between two categories. So if C and D are categories, then a functor f C or D will map objects in C to objects in D, and arrows in C to arrows in D. Cool. So it also maps the not just the objects in it, but the things. Okay, so let me specify this between two categories. This means that for the functor f C to D, the objects of C um, the objects of C are mapped to the objects of D, and the morphisms of C are also mapped onto the morphisms of D. Verbose, yes, but it can help. That's good. That's good. Okay. So the starts and ends of arrows are mapped nicely. If F is an arrow in C from object A to B, so then identities are preserved and composition are preserved in such a way that identities and composition. Making you think for that are preserved. Might expand that later, might not. What is an endofunctor? A functor from a category to itself. Yep, so C equals D. Note that doesn't mean that the endofunctor F doesn't do anything. Just like a function, the real numbers to real numbers still change the numbers. Okay, so that is a very important. So although an endofunctor is defined such that F math cal C right arrow math cal C right arrow. Should I use different symbols for this? Math cal, probably. Let's add those then. Boom, bap, pow, bada bida bang, boom, boom. Yeah. So this does not mean that the contents or constituents, spell that correctly, of C of the category C are not modified. So this is an important note. I will put this in an important box. Or warning even. Yeah. So what's a Haskell functor? What is known as a functor in Haskell is actually an endofunctor on the category Hask. Okay, so functors are always endofunctors. Really? I mean, I kind of like observe that. That's interesting. Okay, so then we call that Hask has types as its objects. Oh no, makes sense. Because like yeah, it's like so like when I say Haskell is limited, functors cannot act outside of their domain, which is Hask, as well as not being able to enforce the laws. But like that's another limitation. I mean, not that you need to go outside of Hask because it's one language. Would it be cool though if you could like map from one language to another? That'd be sick. We call that Hask has types as its objects and functions between these types as its arrows. Yeah, it shows the definition. Uh, they should satisfy the following laws. This does not mean that they do. List is a functor. List is a type constructor that, given some type A, will give you a type list of A. Yeah. Um, where's that defined, though? Namely, lists consisting of types of value type A. This is a type object mapping part. The function mapping part is fmap, given some, okay, map. Yeah, because map is used to map over lists. Given some function fa to b. It give you a function fmap fa to b, okay? Namely, the function that applies f to every multiple list value type A. Yeah. So, yeah, is ID must be globally defined, no? So I close the Haskell playground, but if I open it again, if I have a function like an fmap ID of 1 to 5, does that compile? Yeah, so ID is a global thing. And I assume it works for map as well. Yeah. I mean fmap on a list is basically the same as a map. I don't think there's a single difference. Um, but the same cannot be said for maybe. So like this works because ID is there, but I don't think I can map. Yeah, not valid. But okay, ID is conserved. It's interesting. I could even do like I don't know, um like +3 ID. Why not? I guess. That's cool. Maybe it's a functor. So it is. What's the category of endofunctors? Okay, so first we talk about natural transformations, which are basically arrows between functors. Then we'll use this to build a category of endofunctors, and finally look at examples. So natural transformations. If you have a category C and D and functors FG to C and D, between them, you can also sometimes find so-called natural transformations. A natural transformation, which is a double arrow, okay, is a family of arrows in D that satisfy two requirements. The arrows T go from the results of F to the results of G. For every arrow F and C, same as applying T first. Okay, so this is sensitivity, or commutativity, I guess. Commutativity. Of course, there's a special case where F and G are endofunctors, so C equals D. Um, okay, so now for some category C, we have a bunch of endofunctors on C. And we have natural transformations between those endofunctors. We can make this into a category. Okay, so there's the endo C, the category whose objects are endofunctors on C, and whose wait, this is endomorphisms, right? I just realized. So that must also be a thing, and whose arrows are natural transformations between these endofunctors. You can check the composition of. Okay, so functors are endofunctors in Haskell. Its arrows are transformations from one functor to another. So if f and g are functors, then we're looking for some set of functions t such that for every type A, we have a function f of a to g of a. Yes. Yeah, like change the wrapping type, I guess. Like maybe a to list of a. Let's pick f equals maybe and g equals empty list. So yeah, so maybe to list. Okay, okay. But is it natural? Yes, apparently they are the same. Okay. So yes, the same. Maybe to list is a natural transformation. Okay, that's cool. I didn't realize you could actually represent those in Haskell. Concats. Ah, true, true. It's a list of lists. It's a natural. Okay, so a monoid. Okay. First, look at the classical concept of monoid set theory. Ugh. Yeah. So there's the one in set theory. Okay, so I was correct to look into set theories one. And even probably should have started there. And then we'll also look at an example of such a monoid Haskell. Okay, so then you have to generalize it to set theory from set theory to category theory, and then realize that what we're missing a category theoretic ingredient, a monoidal category, and then with that we can understand a monoid in a category. So in classical set theory, a monoid is a set M with some binary operation satisfying the following properties. So there's associativity and the identity. So is this no? This is not the composition. Composition. An example of a monoid is a set of all finite strings over some alphabet with string concatenation as a monoid. So for every type A, the type list of A is a monoid with plus plus. Yep. Concatenation. Yes. That's why usually there's like mconcat as the monoid operation and the empty list as an identity element. So mconcat for strings is a function that is a monoid. Small note, technically the type list of A also includes infinite lists for which concatenation is not defined. Because of this, list in Haskell technically aren't monads. Monoids. Nor the monads, we will ignore this technicality in what follows. Okay, in category theory. Category theorists are allergic to sets. That's funny. If they see a definition of a mathematical object that includes the word set, then immediately start thinking about how they can rewrite this definition without using the word set. I love this. Or respectfully, they'll try to generalize, yes, the definition such that it holds in categories other than sets too. So again, like the whole set theory thing, man, it's obvious how to begin. The set M should be replaced by an arbitrary object M in some category C. Yep, the binary operation boop should be replaced by the arrow. Okay, yeah, so it is just a binary operation. So why is it defined so? Why do they explain it so weirdly on Wikipedia? Like if I look at a monoid, so this is just a binary operation multiplication, and this is an identity called unit. I think that's safe to say. So similarly, since you can't like open an object in a category, you can't say what it is. We have to replace the identity element with some arrow going into M. The arrow move should clearly end at M, but where should it start? Okay. Uh, tensor product in a monoidal category. So the aim here is to define some operation, this multiplication, that will allow us to combine two objects A and B in some category C into a new object A x B in that same category. This is okay. The natural way to map objects in categories is the functors, but in this case we have to map two objects into one object. We need a functor that can take two arguments. Can functors not? I thought morphisms could do that, no? The typical way of solving this is by instead introducing a product space that encodes both arguments as one. So we need to have an object AB, okay, and some category, product category C times C. At this point, you may think I'm going crazy. In order to define monads and categories, we need to define products of objects. But to do that, we need to define monadal categories. But in order to do that, we need to define products of whole categories. That's right. Luckily, it's quite simple. For categories C and D, and the product category C times D, is simply the category whose objects are pairs A and B of objects A and C and B and D, and whose arrows are pairs A, B to X, Y of arrows A to X and B to Y in C and D. Okay, respectively. Composition works straightforwardly. Fg of K and L equals F of K, G of L. I kind of saw this, okay, with sensitivity easy to check. Yeah, I don't know how to write this honestly in my notes, but I'm kind of picking up what I put it down. Okay, so The machinery of functors is available to us again. That combines objects and arrows. What properties would we want this function to possess? Well, would certainly want it to be associative in some way. We want A cross B cross C, yep, to be similar. Okay, but not equal. This can be made precise by saying that there is a natural transformation whose components are isomorphisms. I see. So you have alpha, which is this to this, some mapping of this to this. Similarly, we like there to be some identity element for this. Let's call it I. We want I. Okay, I saw this in the diagram of monoids. On Wikipedia, it had the I thing, like say. We want I cross A and A cross I to be similar to A. But why similar? Not equal. This can again be made precise by saying that there are natural transformations whose components are isomorphisms. So lambda. So I, yep, A and A. Okay. Oh, so this is lambda under rho. Okay, now I understand that. There's some additional conditions about these natural transformations. Playing next with each other, the coherence conditions, let's go for that. If you compare this section to the one about monoids and set theory, you could probably spot some similarities. So yeah, we have, instead of elements in a set, we have objects in a category. Instead of the binding operation, we have the functor this. So this is a functor, which is multiplication. And instead of equations involving a set, we have natural transformations between functors built using this. This correspondence is why the term monoid is reused and why this concept is called a monoidal category. Right, so if we look at the page again. Well, actually, let's go back to monoid first. Here, yeah. So you have this. Lambda is connects I cross m to this, and m cross I is rho to this. And you have eta cross 1 and 1 cross eta, both of you giving m cross m. What's eta do again? Eta is the unit, which maps I to m. So I guess it makes sense because like I becomes m here. If I can kind of read it, and then you have mu, which I guess it kind of consolidates it, like kind of flattens it in a way. Um, in a way, strong emphasis on that in a way. So the monoidal category, okay, is C that. So monoids in a monoidal category. Above we define a concept analogous to monoids. However, it is not quite what we're looking for. This is the math subreddit, by the way. The math subreddit. I thought it might be like functional programming, but no. Which is cool. However, it's not quite what we're looking for. Okay, and a monoidal category is a category with some additional properties. What we're looking for is an object in a category satisfying certain properties, namely a monoid in a monoidal category. We start with the definition of a monoid and swap out set theoretic concepts for category theoretic ones. So a monoid in a monoidal category is an object M with an arrow such that M cross M, or M times M, is mapped to M, multiplication, and an arrow eta units to monoid axioms. So there's associativity, okay, and unit. So how about a monoid in the category of endofunctors? Okay, now we know what a monoid is, and a monoidal category is, we can start thinking about a monoid in the category of endofunctors. As you found out above, we first need to find a monoidal structure in the category of endofunctors. Turns out that's pretty easy. Composition of endofunctors satisfies all the properties of a tensor product. What is it? What is a tensor product? I hear this used. It's this. It's literally this. Okay, it's a vector. Okay, it's a vector spaces, I guess, or fields. But okay, composition of endofunctors satisfies all the properties of a tensor product. It turns out The tensor product entity I is simply the entity functor ID. It takes a little bit of work to show that the natural transformations behave the right way, but we'll skip over that here. Okay, fine. So then a monoid in the category of endofunctors is some endofunctor M, a natural transformation, and a natural transformation eta, so eta and me, that satisfy the monoid axioms. Okay, that's it. But M doesn't M need to map to itself? How can we make this sense of this definition? Well, here's one way that will carry over quite nicely to Haskell. We can think of our endofunctors as introducing some additional structure on the objects they're applied to. The action of the endofunctors on arrows is to lift the arrow into the structure. The endofunctor M then is simply some chosen structure. The transformation mu can be seen as flattening the duplicate structure, okay, of M down to just structure M. Okay, so is a monoid like if I have just 5 and just 3 and the transformation eta can be thought of as injecting unstructured data into the structure M. If you have a triplicate structure m.m.m, it doesn't matter if you flatten it down to m as m.m.m.m.m. Yeah, cool. Unit is identity of multiplication. Okay. Let's move to the build of Haskell again. As before, we looked at into Hask. What is from here? Okay. So let's use that M is a list. What should we pick for mu? It should be a natural transformation from a list of lists to a list of A. Okay, concat, yes. How about eta? It should be a natural transformation, so the ID of A to list of A. Okay, so it's not the identity function per se. It's more like it wraps it. I guess this is like analogous to, if not equal, to like the return function in Haskell or pure. Like if you do return on an object, it wraps it in an IO. If you do, or same for pure. I mean, I think it depends on the context, but like if you do just, I guess as well is the ID function. Okay. Um, which is cool. And then I don't know about this though. Like if it's an endofunctor, does that just mean that the first argument is the same? Maybe? I don't know. Concat is join. Okay, so concat is joining to yeah. The that's the end of the post. The function is also known as pure or return Haskell. Okay. Pre-read. What about the monoid axioms? Well, for associativity, okay. So concat equals concat equals concat.map concat. Sure. Does our choice of unit play nice at the multiplication? Hmm. A list of list to a list. A list to a list. A list of A, sorry, to a list of A. Okay. Injecting every element of a list into a list and concatenating is the same as doing nothing to the list. Okay. So list is a monoid in the endo task. Or equivalently is a monad task. Hooray. Okay. Sure. I kind of missed the whole point where like we I guess I mean a monad is just a definition. So we're just proving that monoid is indeed, or at least in this case, this type of monad. This type of monoid is in the category of endofunctors. Okay. Yes. And look at that. This links to this. Who'd have thought? Reading this post reminded me of the existence of coherence conditions in monodal categories. Oh yeah, this is an operator, isn't it? I don't know. I didn't know what I'm looking at. I want to die. Oh man, that's funny. Hmm. So binds combines fmap and join. Join takes a monoid of a monoid of A and fattens it. Sure. I mean, I don't know if that's a monoid per se, but like, yeah, like a type of type. And this takes, in this case, they're using M instead of F, which is interesting. Uh, hmm. Yeah, because like the main difference between bind and fmap is that first of all these are reversed, but like that's not too hard. Just reverse the arguments, I guess. But also, or sorry, swap the arguments. Like it's not a big deal. But also this this wraps it. This doesn't. But they both have the same return type, which is a bit strange. Obviously, it's the inner workings of fmap. Like looking at the type signature alone isn't enough. Um, ma binded to f equals join fmap. So it's literally just join on fmap. Okay, but fmap returns. But you do it on the ma. Yeah, but fmap returns just mb. You know. So how is this a valid input? Yeah. Okay. I don't know. What? So there's whole proof for it. Man, okay, so this stuff is deep. Well, thank you, Reddit. That kind of helped a bit. So yeah, I guess the main thing then is to just read this book. And that's like that'll probably help it more. But at that point, I don't know if how much it helps. I mean, let's have a look right now. Who needs types? Good question. I love that question. Monod as a set, monod as a category. Ah, great. Straight into monoids. What the f? Holy C++. Um, this is 2019, yeah? Concepts, yeah. Concepts are great. Dude, I didn't realize that you could actually do this in concepts. That's cool. That is awesome. I mean, proposed. I don't know if they're in the language yet. This is 29. This is 2019. Concepts are C++ 20, I think. So they should be out by now. Um, that's cool. MMT. Okay. Seeing it in C++ actually helps me because I'm just more used to its syntax. So it just takes for an STD string. This is a special overload or specialization here. It's literally just returning an empty string. I mean, I would expect nothing less from something called mempty, but whatever. And append returns these plus this, which takes two things and combines them. Um, why is that different from Haskell? Cause I think Haskell takes a list of lists, right? Like a list of strings as opposed to just two arguments. I could be wrong. Um, I'll look it up actually before I speak further. Data.monoid. Concat. Oh, that's different. Mpen's different. Mpen takes an A and an N, which is an A. Concat is different. That's for joining. Does it say here? Is there a concat? No, there isn't a concat. Okay. Okay. There's a lot to read here. I mean, the whole book is a whole book. So I think I'm going to end the video here. But okay. I said I would stop when I understood what a monad was. A monad, as in a monoid in the category of endofunctors. I do understand what an endofunctor is. That much I can say. Maybe not like perfectly, but I definitely understand how it functions, or how it endofunctors, I should say. And I also understand a monoid in that it's a category with a single object and it has these two functors, I guess, with the unit, which is kind of like the identity, but not really, and the binary operation, which is multiplication. Don't fully understand that, but then like I do understand how like a monad derives from it and just being an endofunctor, and like yeah, very interesting. And obviously I know how to use a monad in programming. Like the like learning the use case is a lot easier than learning the why, like how it's defined. Um, but cool. Yeah, so it's been 3.5 hours. It's now 3 a.m. and I feel a lot smarter for it. Let's go ahead and just consolidate our notes here then. Uh, by which I mean move them into my wiki. For Obsidian, for my Obsidian, I have a format where I have loose like a draft notes, and then I move them into my main wiki notes afterwards. So let's move all of these. Close this down. I actually have so many. Oh my god. Uh, yeah, can move all these. Identity, associativity. I actually made a lot of quite a lot of progress today. I'm very happy. Oh camel, soon. Yeah. And then let's see if we can look at my tree here. Holy moly. Uh, Haskell. Functor. Here we go. Category theory. So what we got? We got category theory links to functional programming, functor, mathematics, morphism, monoid. Morphism has all these different things. Cool. Got quite a lot. Set theory has a lot. Functions obviously have a lot. Computer science, maths. Yeah, funny how maths is bigger than computer science in my thing. And Haskell is also massive. Cool though. Yeah, I like to see it. Anyway, if you, well, I doubt anyone watched this entire thing. But yeah, that was cool. Um, yeah, if you're watching this right now, awesome. Thanks for sticking well, thanks for sticking along with skipping ahead or whatever. Hopefully there was something interesting here. Um, as I try to learn, hopefully you can also learn some stuff too. I do intend to go through this book at some point. Although when I do that, I don't know. I might record a video going through it. I don't know. I mean, the good thing about recording videos is that it's good to A, look at in retrospect, and also B, I can use them as footage later if I want to make a YouTube video on the main channel. Um, but yeah, I mean, I could read that, but right now I want to read this book, Clean Code, the infamous. And I also want to read this book, The Semantics of Programming Languages. Don't know how far I'll get in this, but like semantics is something that I really struggle to understand. Like I just don't understand. Like yeah, I just don't understand it. But it sounds like it would be interesting. Same with like formal linguistics. I'm very interested in linguistics, but the formal study of it, like all the syntax and stuff, I have not managed to wrap my head around yet. Unfortunately, we don't cover it in our university courses because that stuff's just too, I guess uni is too simple. Um, but I would like to get into that at some point if I can. So yeah, thanks for stopping by. And remember, a monad is simply a monoid in the category of endofunctors. What's the problem?